We have looked at the mean vector of a transformed random variable, a linearly transformed random vector, and we have looked at the correlation and covariance matrices. But what about the distribution? The most important thing about a random variable or a random vector is the distribution. So the question is there a way to obtain the distribution of the transformed random vector in terms of the joint distribution of the random vector x, uh, for which we can compute the distribution of y. Uh, Again, we are obviously assuming we have a linear transformation, so random vector y is equal to some matrix times random variable random vector x. For simplicity, we will just consider the case where y and x are of dimension 2 and the transformation matrix A therefore is a 2 by 2 square matrix, and we will assume it's invertible. If it is not, occasionally it becomes easier to write the some of the components separately, or you can do a reduction in the dimension, because when A is not invertible, that means at least one component of X can be written directly as a linear combination of the remaining components of X. So you can just set it apart and consider it differently, consider it separately. But in the general case, we will assume matrix A is invertible, and if it is not, you can treat it in a different way. And then I will just conclude this by saying that this is generalizable to more than two dimensions, but the approach is in general the same. So what we do here is observing the effect of a linear transformation on a random vector in the special case where the random vector is of size 2. Now here on the left hand side you see the x1, x2 plane, and assume that the shaded region you see here is an infinitesimal area. Okay, so this here is dx1, and this distance here is dx2, and therefore the area is dx1 dx2, and we will look at the random vector x, the probability that the random vector x lies in this infinitesimal area. And well, this point here is x1, x2, and obviously when you move by dx1 in x1 dimension, you get x plus dx1, x2. Similarly, you have x1, x2 plus dx2 at this point, and this one is x1 plus dx1, x2 plus dx2. And the area here is, of course, dx1, dx2. Okay? So remember, similar to a single random variable, we can write the joint PDF at this point multiplied by this infinitesimal area gives me, at the limit where dx1 dx2 goes to 0, it will give me the probability that x is in the vicinity of the point x1 x2. Okay, so that will be our main point. Now when you apply the linear transformation defined here, okay, to these four points or vectors, these points are vectors in x1 x2 space. When you apply this transformation to these four vectors, assume that these are the points you get. So x1 x2, this point here, when you apply this transformation, it maps to this point here, y1 y2. And this point here, x1 plus dx1 x2, when you apply this transformation, it maps to this point, right? You can see this by just plugging in here into random vector x, this vector x1 plus dx1, x2. Just put in the values, multiply by the a coefficients, and then using these base relationship that gives me this point, you can see that the transformation of this point here corresponds to something like this. Similarly, this point maps to this point, and this point maps to this point. Okay, since this is a linear transformation, what I get is a parallelogram. Okay, it has a nice shape, so this rectangular region becomes a parallelogram after this transformation. So it's not like I have some wobbly bits here, it's just a straight line. As the name implies, this is a linear transformation. Okay, now the basic observation here will be random vector x being inside the rectangular region is the same event as random vector y being inside the parallelogram, which I obtained by applying the transformation to this rectangular region, because essentially they represent the same outcomes. Okay, so therefore the probability that x1, x2, random vector x, is inside this rectangular region, that can be represented by this expression, the joint PDF at that point times the infinitesimal area, can be that can be written to be equal to this here, the joint PDF at point y1, y2 multiplied by the infinitesimal area of the parallelogram. Now, the area of the parallelogram here we use a result from analytical geometry at this point. The area of this parallelogram is equal to the magnitude of the cross product of these vectors. Okay, you just get two sides here emanating from the same point. You get their cross product. Remember, the cross product gives also a vector, but we just want its magnitude. Okay, so the cross product of this by this will give you a random vector in the third dimension, which is orthogonal to display. Okay, but we are not interested in its direction. We are just interested in its magnitude, which by definition of cross product can be written as this expression. You just write these two vectors as a matrix, and you get their determinant. Okay, so by definition, the area of the parallelogram can be written as the magnitude of the cross product of these two vectors, which when you expand, you get this expression. And this here, this expression here, is the absolute value of the determinant of matrix A, the transformation matrix. And therefore, if I put that to the left-hand side, I can write the joint distribution of y at point y1, y2 as this. The joint PDF of x at x1, x2 divided by the absolute value of the determinant of A, and x1, x2, since we assumed matrix A is invertible, can be written as inverse of A times random vector y1, v2, and y1, y2 evaluated, the joint PDF of x evaluated at this point, which is in fact x1, x2, divided by the absolute value of the determinant of the transformation matrix. And as I said, this can be generalized to more than 2 dimensions.